Okay, so this big lab that I just gave out, needs to say this is not going to get done in one day. Okay, it's going to take us at least today, Tuesday, and Wednesday. Okay, so the good news is, well, that's the good news, good news. It's a cool lab, and each of those nights you're really not going to have hardly any, if no homework at all. So at least you get a little bit of a break with that regard. So let me explain what's going to happen in the different parts of this lab. So let me talk about procedures. So you're going to have a burette. Hopefully you all have done some titrations. It's got the little valve, okay?
It's been a long time.
And that's going to have an unknown molarity of sodium hydroxide. So at each lab station, you are going to have your own bottle of sodium hydroxide. Okay, so everybody's sodium hydroxide is going to be a little bit different. So the first thing that you have to, what? So the first thing that we've got to figure out is what's the molarity of the sodium hydroxide. Okay, that's the first thing you got to deal with. So let's talk about how you're going to handle the burettes. When in lab, here's the golden rule. You always assume that the people that used the lab or the glassware before you were idiots. Okay? It's just good operating procedure. Assume that they were idiots. So the first thing that you want to do is grab that burette and thoroughly rinse that with deionized water. Okay? Rinse it, rinse it, rinse it, open it up, let that run through. Now I'm not saying spend like an hour on it, but just give it a couple good rinses. The next thing you want to do is actually rinse it with sodium hydroxide. The reason that you actually want to rinse it with sodium hydroxide is because if there's water that's in there and you just automatically fill that up with the stock solution, that water will actually dilute that solution. Okay, so that's why you want to rinse that with sodium hydroxide, and that includes opening up the valve and running some through it. So rinse it, open up the valve, run some of your sodium hydroxide through that solution. So once you get that done, then you're going to fill that up to the 0 mark. Fill it up to the top. Now remember, when you're reading liquids in glassware, always read off the bottom, known as the meniscus. Okay, that's what you're going to read off of. So what we've got to figure out is what's the molarity of the sodium hydroxide. So we're going to take advantage of a kind of a cool reaction. So we're going to react something known as KHP. So, and don't write this down. I'm not going to expect you to know the formula. I'm going to write it all out. Okay? So it's KC, it's big long organic compound, H8, H4O4. Now, the beauty of this is because there's an element of group 1 in it, it's soluble. Okay? So you're going to take this, and when it reacts with sodium hydroxide, basically what happens is this. That sodium reacts and kicks out one of the sodiums. So as long as there's sodium hydroxide available and there's KHP available, these things are going to react. So you're going to take, and on the instructions it says to use like an Erlenmeyer flask. You can just use like a 100 milliliter beaker or 250 milliliter beaker. You don't have to use an Erlenmeyer flask. So what you're going to do is you're going to take a beaker. Now, let me explain and show you the times when you have to be precise in these labs and when you don't. So if you look over here on your lab, on this second to the last page where it has this diagram right here, and you're going to do part B, the standardization of the sodium hydroxide solution. So this is where you're going to use the water that you boiled yesterday. We boiled that water yesterday to get any carbon dioxide that was in it out. Because carbon dioxide forms carbonic acid which could react and alter the results. Not a huge amount, but it's enough that it could be potentially significant. So that's why we boiled that water yesterday, to get rid of that. Now, notice on here, down here about halfway, it says, add to each sample about 100 milliliters of water. Notice that that does not say 100.00 milliliters. So when you see in a lab, you see add 100 milliliters, don't spend huge amounts of time trying to get exactly 100. And here's an indicator. When you say it says about 100, all we're using the water to do is dissolve the KHP. And since it says at about 100, what that tells me is that I'm not going to use that 100 milliliters of water in any calculation going forward. If I needed that volume of water later on, I would, hey, I need to measure that to be 100.00. So all the water is doing is allowing the KHP to dissolve. That's it. That's all it's doing. So the 100 milliliters is not something that you are going to write down. All you're doing is dissolving. So you're going to do this 3 different times. You're going to try a sample of about 0.4 grams of KHP, 0.5, and 0.6. That is not 0.04, okay? That's 0.4, 0.5, and 0.6. The mass doesn't matter, as long as it's something around 0.4, something around 0.5, something around 0.6. So, let me see that fuchsia piece of paper. So, where you're going to record this standardization of your sodium hydroxide solution. So, trial 1, this is where you're going to record the mass of your KHP. The scales that you are going to use, and I'll show you when we get over there, are extremely sensitive. These scales go out to 4 decimal places, okay? Which means these are incredibly sensitive. This is why they are in glass cases, because if there's air coming out of the vents, they are so sensitive that the air from the vents would give you a false reading. That means they're also very expensive, okay? So don't put your hand on there and go, oh, what does my hand weigh? No, stop, okay? These are incredibly sensitive scales, okay? They work the same way before. Put on your little weighing dish, press the tare button. So in this situation, don't sit there and spend 5 minutes counting out little granules to get exactly 0.4. No, stop. Okay? Get something around 0.4, 0.4186. Just get something around there. Okay? Then you're going to get something around 0.5. And then you're going to get something around 0.6. Okay? You're going to do 3 different trials. Okay? So imagine this, you have your KHP. You have your beaker, which you have rinsed with distilled water to make sure that there's no impurities in it. And then you've added about 100 milliliters of that carbon-free water that you all created yesterday. So in here, you've got the 100 milliliters of the boiled water. You could even use the mark on the beaker. If it says 100 milliliters, you can just use that to get an idea. You don't even have to take a graduated cylinder and measure out 100. You can literally just use the mark on the beaker. Just get 100. Then you're going to add the KHP to that, okay? This is what's going to go on the magnetic stirrers. Y'all worked with magnetic stirrers before.
Yes.
Okay? All right? They're out. There's going to be a little white magnet on it. Okay? I know that they spin. Don't put it on there and turn it on to high and go, look, Mr. Burkamp, it spins.
I
needed to turn it on. I was talking about.
He's not the brightest.
So drop the magnet, wash the magnet so there's no contaminants on the magnet. Drop the magnet in there, put it on the stirrer. Then you're going to begin to, what you're going to begin to do is then you're going to add sodium hydroxide. So what's gonna happen, and more importantly, you need to add 3 or 4 drops of phenolphthalein. Phenolphthalein turns what color when it turns basic? Magenta. Okay? You're gonna have bottles of phenolphthalein at your table. So it should look like this. Might not even be that dark. That's awfully dark. So here's going to be the reaction. Basically, KHP is going to react with the sodium hydroxide to form water and another compound. Here's the point of the story. Everything is in a 1-to-1 ratio. Okay? So here's the stoich that I want done. Right here where it says, so calculations to trial 1 to obtain the molarity, labeling every value. South people, you see what I want. Okay? Not random numbers, Gapshon. Okay? None of that sketchy stuff that you think is stoich. So, here's how you're going to start. The molar mass of KHP is 204.2 grams per mole. Okay, write that number down. You're going to need it. Okay, 204.2. So, here's going to be the math. You're going to start off and you're going to go 0.4, whatever grams of KHP you're going to have. Okay? Now, what you're ultimately after is the molarity of the sodium hydroxide. So basically, what's going to happen is that as long as there is KHP in the solution, when you add sodium hydroxide, it's going to get reacted. Okay? So what you need to do up here is record the initial and final burette readings. Okay? If you're clever, just fill it up so it starts up there at the top. Okay? And then you're going to add sodium hydroxide. And the first one always takes a while because you're not sure where it's going to end up. But initially, you can probably add like 2 milliliters at a time. Because what you'll see is that the closer it gets to running out of KHP, the pink color will last a little bit longer every time that you add sodium hydroxide.
What?
Stop. So, as it gets closer and closer, when you add sodium hydroxide, that color will last just a little bit longer. Eventually what will happen is that, and don't overshoot it because you can't go backwards. So you want to add sodium hydroxide until that ends up with just a faint hint of pink. Because what that means is that you've used up all the KHP and then the sodium hydroxide goes into the solution and there's no KHP for it to react with, and therefore it ends up being a basic solution. So as long as there's KHP to react with, it stays clear. As soon as the KHP is used up, then you know, hey, this is all gone. So this is where it plays into the stoich. So you've got 0.4 grams of KHP. You know, the molar mass of KHP is 204.2 grams of KHP. That's equivalent to 1 mole of KHP. Now, everything's in a 1-to-1 ratio. Cool. So I know 1 mole of KHP is going to react with 1 mole of sodium hydroxide. So if I stop right now, what am I going to have?
Moles of sodium hydroxide.
Moles of sodium hydroxide. I want molarity. So what do I need to divide by?
How many milliliters the difference is in your initial and final purity?
Yeah, so you're going to divide by the volume in liters of however much sodium hydroxide that you added. So your last step out here is going to be divide by however many liters that you used. Okay? So let's say it was 25 milliliters. So that would be 0.025 liters. And that's going to generate for you that. I don't need to see all 3 calculations, but I want to see one calculation like this, okay? The only thing that's gonna change is this step right here and the volume at the end. Everything else is gonna stay the same. So basically, the shortcut is you're gonna divide by 204.2, and then you're gonna divide by the volume in liters. Okay, that's the shortcut version. Now, eventually you wanna find, so you're gonna find 3 different molarities of the sodium hydroxide. If we can get through that today, that would be great. Okay? Any questions? Now, I know there's a lot of people gone, so if your lab partner's gone and you want to work with somebody else for today, that's cool. But just keep in mind that each kind of bottle all the molarities should be pretty much about the same, but there might be some variations. So anyway, just keep that in mind. All right, let's go do chemistry. Kevin, stop that camera, please. Huh?